All right. Now, I did make the comment, I totally was ripping on von Neumann the other day at the end, which is like it's totally impractical. Well, I still kind of believe that. However, the most important thing is really is not so much whether you can actually calculate the CFL boundary. That's not what's important. What's important about the CFL ultimately is what is the relationship between time step, space step? How much more is it going to cost you if you want better resolution? That's it. Because ultimately, how do you choose a scheme, and what are you doing at choosing a scheme? You're going to say, I'm going to discretize. Your first thing is you discretize space. In doing that, you're already saying, I get to pick dx. I pick accuracy. Once you pick accuracy, it forces you to pick delta t. Okay, and you need to know how to scale those relative to each other. So let me do another example. I'm going to do hyperdiffusion problem. So this is higher order diffusion. Here's what the equation looks like. Instead of 2 spatial derivative, it's 4. It's still a very simple looking equation. I still can write down the exact solution to this without much problem or effort. And what I'm going to do is discretize. So first, let's discretize spatially. So you can say, okay, du dn dt is equal to minus c. Fourth derivative. I give this to you in one of your tables earlier on. I think I do. I'm pretty sure. I give you up to 4 derivatives. Here's what it looks like. un plus 2 minus 4un plus 1 plus 6un plus minus 4 un minus 1 plus un minus 2 all over delta x to the 4. Every time you get a derivative up there, so you're seeing a pattern here. 2 derivatives had a delta x squared on the bottom. How many do you think 3 derivatives has? Delta x cubed and delta x4. Now, big deal. You'd say, I don't care. But if I now discretize time, and let's do the time in a Ford-Euler way, because Ford-Euler seems to work well with diffusion equations, then we get the following equation. My point in the future is what it is now. Plus, or actually, the way it works out is minus lambda. I use my neighbor point, my other neighbor point, use myself. Oh, geez. Okay, hold on. I'm trying to fit it all in one line, and I'm minus my other neighbor and plus my other neighbor. All of these evaluated at m, current time. I know that looks a little mushed up, but there it is. It's a scheme. You can do it. And your lambda talk about a crushing blow. You pick your accuracy, you want to double it. It's not good enough. You say, how much more is it going to cost me now with higher hyperdiffusion? Double the accuracy. Gives me a factor of 1/2 here. Right? So you're going to have to, 1/2 raised to the 4th power, that's going to give you a factor of 16. That means you're going to have to take delta t down by a factor of 16. So a factor of 16, and you have twice the amount of points, 32 times slower. Okay? All right, so times 8 seems like child's play. Because here, when you have higher derivatives, you see what's going to go on here? This is what's called numerical stiffness. Okay? The problem starts to become stiff, brittle, whatever you want to call it. This, I didn't make this up. You got to keep taking smaller and smaller and smaller steps to make this thing actually work. Okay? And that's your scaling. So the CFL tells you everything you need, right? You want to double your accuracy. drop your step down by a factor of 16. That hurts in performance. Okay?
To get more accurate is prohibitive? Is that?
Yeah, so the bigger this difference is here, the higher this power relative to this, that's what's killing you, right? Is, you know, if I have a sixth order scheme, this goes delta x 6, delta, so the relationship between delta t and delta x is the measure of numerical stiffness. Okay, so this is a really important problem to think about dealing with, because it really comes up in a lot of systems. A lot of people have hyperdiffusion in their systems. Some people put hyperdiffusion in many systems just to do what's called regularization. I don't know if you've heard that term, but what it is, you say, I have this equation, and you know what I want to do? I kind of believe that all this really high frequency stuff is sort of junk, and I want to filter it. So a lot of people say, well, I'm just put a big hyperdiffusion filter on there. All it does is kills off high frequencies. So a lot of codes have hyperdiffusion in it to sort of act as a filter, very much like when you do the Lax-Winthrop scheme, right? There's artificial diffusion in there just to try to stabilize the scheme. So people will say, I can stabilize it by throwing in, you know, make this epsilon. I'll make it small. But the point is, you still have this constraint going on. Okay? So that's a very standard technique in stabilizing schemes. So if I can't calculate the CFL number and the scheme seems to be a little squirrely, throw some diffusion on it. A little bit, higher derivative, helps filter out growth modes. That's a pretty standard technique. Yeah?
Isn't there an ODE in MATLAB designed for stiff functions?
Yes!
How does that manage this?
Rocks it. I'm going to talk about that, actually. I'm getting to that. Dude, you're looking ahead in the script. Shh. You're giving away the ending. God. Okay, we're going to talk about that, actually. So, by the way, I'm going to make one other point first, and let's get to how to handle this. By the way, but just real quickly on that issue, which is there is some OD, so there's OD415S, OD113, and their purpose is, if you remember, this is killing you for stiffness, and what it's really doing to you is it's limiting your delta T step. This is why implicit schemes have survived and why people like them, right? An implicit scheme, if you remember when we did Euler, backward Euler on the wave, if you do backward Euler on equations like this, you can take huge steps, and sometimes you don't even have CFL restraints. Backward Euler rocks. It's an implicit scheme. You can take big steps. Great. But you pay a price for doing an implicit scheme, right? Because you're trying to evaluate the right-hand side in the future. But you can then maybe take any step you want here. So all you have to do is say, all I have to do is take care of accuracy and then step forward. I don't have to even think about having troubles. But that's hard, so you do predictor-corrector methods, right? You predict the future, so you sort of do a semi-implicit scheme. That's what predictor-corrector does, and that's OD113, for instance. And you can get much fancier with schemes like that. Now, the one thing that this seems to illustrate is, this is a problem from discretization, right? It doesn't seem to be a problem. Like, it's just all about how I discretized. You know, if I do a discretization, I get the delta x to the fourth. I do pseudoderivatives, delta x squared. So this is about doing Taylor expansions and the problems that arise there. So I want to illustrate to you that, in fact, it's not just about Taylor expansions. It's really about the derivative.